Okay, thank you for invitation and giving me opportunity of this talk. So this talk is about how to construct or how to find finite dimensional representations from property of random walks via functional analysis. The introduction, we already many times heard the introduction. It's a first of all, our group G is finitely generated. Even though almost all theory works equally well for locally compact group, which is compactly generated, but I concentrate myself on finitely generated group. And for simplicity, I consider S contains neutral element and it's symmetric. And because I talk about random walk, I fix a probability measure mu on G, which is symmetric, so mu x has the same value as mu x inverse. And the support mu is S, that is support is finite and it's generate for group G. The motivating theorem is Gromov theorem. That if G has polynomial growth, that is if there's a D in such that limit, or because limit may or may not exist, one can take limit sup or in, and in Gromov case it was sup, but limit doesn't matter in fact. Theory works equally well. Of the growth of this ball of radius n divided by n to it grows at most polynomially. Then the conclusion is that the G is virtually nilpotent. So this is a theorem that input condition is a geometric condition or analytic condition, and the conclusion is algebraic structure. This is what we are interested in. And the proof, also proof was hard, and Gromov's proof was sophisticated. But the first step was that the last step is induction. So it suffices to show there is a virtual quotient onto Z, or quotient onto virtual Z. So virtual Z quotient. That is G has finite index subgroup, which surject onto Z by homomorphism. Because the reason is that then the kernel of this homomorphism has polynomial growth. Is first of all, it's finitely generated because of some reasons. It's finitely generated and has polynomial growth of degree. That is, this D decreases at least 1 because of this Z factor. And then by induction, this is nilpotent, and then it's a problem becomes problem about solvable group, and it was already solved at that time by other people. And then the Gromov's proof of finding this virtual quotient was very sophisticated, and later new proof was second proof was found only in 2007 or 8 by Kleiner. who used rather elementary but difficult but hard method. And then there was a proof by Shalom Tao, which is really finitely, and Khrushchevsky and VR Green Tao. Already VR gave a lecture on that. And also I gave myself a simple proof in 2015. So how to find this virtual quotient is virtual quotient onto Z is that one use Titz alternative, or rather consequence of Titz alternative. That's any finitely generated amenable. I hope everybody knows what amenability means. Anyway, if group has polynomial growth, then this group is amenable. And any finitely generated amenable group, which is linear, is virtually solvable. So that if it's even if it's more or infinite group, then this is virtually solvable. So it has a virtual Z quotient that's up to finite index, it's solvable, and it has an infinite abelianization, and because it's finitely generated, it has a Z factor. So now the problem becomes that so if G has infinite linear representation, then it's done. So one wants to find non-trivial meaning infinite linear finite dimensional representation. And Shalom's idea was to actually this the whole scheme was built by Shalom. If the Shalom wanted to find a new proof of Gromov's theorem, it was a time before Kleiner found the second proof. He wanted to use reduced cohomology for this purpose. Reduced cohomology was introduced much older. It's introduced sometime in 70s. So the starting point is any representation. Oh, but in my talk, representation is always representation of Hilbert space. So and the theory equally works for orthogonal or unitary, but for some reasons I use orthogonal representation because probabilities use probabilistic tool. One always need real number. So orthogonal. So orthogonal representation always exists. A lot of orthogonal representation exists. So this need not be finite dimensional. Then one considers the space of cocycles. Cocycle is a map from G into H, because G is discrete, there's no topology. If there's topology, it's a continuous map. Is a cocycle, any map is more precisely one cocycle. If it satisfies one cocycle identity. One cocycle identity is that BGT. GT is in the group G. As of this satisfies writing to any GT. Okay. And this is, although I don't use this factor, if you are, there are too many reasons why we consider this for one cocycle. But one reason is that this is one cocycle if and only if map such that rho G maps vector B to IGB. This is orthogonal representation, but there's a linear translation. This map is G to this rho G is affine action. And any isometric action on Hilbert space is of this form when the space is real. And then there's of course notion of one coboundary is one coboundary or coboundary. Is that given by vector V in H? That's this is V minus IG. V is some vector. And its well-known fact is that it's a coboundary if and only if it's bounded. So this obviously bounded. The norm is bounded by 2 times norm of B. And if B is bounded, then it's actually of this form. And now the space of cocycles is a Hilbert space. With respect to inner product or norm, I write norm. With respect to B norm square is defined by the mu average of this norm of BG. I use the notation like average like this. This is integration with respect to T. Mu average. Oh, just mu average, yes. And if it's it's easy to figure out what is the input. This is a Hilbert space, and the cohomology, first cohomology of this representation pi is defined by cocycle over modulo coboundary. Coboundary is given by this, yeah. But then this is a Hilbert space, and this is a Hilbert space. But this one is not closed in Z space of cocycles because this may pointwisely converge to some unbounded cocycle. So it's in functional analysis you don't want to take a quotient by something non-closed subspace because it's pathological. So one takes closure of this B. So this closure is the same as Hilbert space closure or the pointwise closure. I should have pointed out that because of the cocycle identity, if B is 0 on the set of generators, then the B is 0 everywhere. So this is really a norm. And this is pointwise topology and norm topology coincide. And because it's Hilbert space, the quotient by subspace is canonically isomorphic to the orthogonal complement in the Hilbert space. And in fact, one can check not so difficult. No, if you want to check, you can easily check. This is a harmonic cocycle. So this part is abstract, and this part depends on mu, but they are always isomorphic. Whereas B is harmonic, or more precisely mu harmonic. By definition, it's mu average of B GP is BG for any G. Or BGT is BG plus pi G BT, and the mu average of BG is BG. So it cancels, and the mu average of BT is 0. And BE is always 0 for any cocycle. So this is if and only BT is 0. Just G is identity, G is neutral. It's simpler. Then there's a theorem. Oh. In fact, I don't know who really to attribute. Mock, Prof. Shalom. Shalom. Something 95, 97, 99. That's if G is finitely generated. If G is finitely generated and not property T, in particular amenable, if you don't know property T, it's true for finite amenable group. Finitely generated non-T, then in particular it's not finite group. Then there is a height such that the H1 bar is not non-zero. In fact, it's if and only for finitely generated group.
So H1 bar is
yeah. Oh yeah, bar. I forgot. Yes, sorry. Thank you. Okay. By the way, it's easy to find the pattern orthogonal complement. You need just a small calculation, but it's rather easy to check that how many one coboundaries are 0 on your exercise. How many one coboundaries are 0. That's so the coboundaries are of this form. If it's harmonic, then the V is mu average of pi G V. But the Hilbert space is strictly convex. So this happens only if V is pi G V for any G in generating set. So for all G in all group, V is pi G in one. Therefore, this cocycle was 0. Coboundary was 0. Now I will present the explicit construction of this pi. Will be given later at the end of the talk. Now for reduced cohomology, there's an important property of Shalom property. So that in general, I want to so there exists pi. So this is existential statement, and I want to learn what is pi, what is what does pi look like? Or pi, or because it's only the cocycle part, only cocycle part is important, and you can add some redundancy to pi, so that I don't want to see the redundancy. So the pi restricted to the span of BG. So span of BG is invariant under pi. That this formula says pi g bt is BGT minus BG. So span pi g BG is G invariant subspace, and we only look at this representation. What is this? In general, pi decomposes as a direct sum of, this is just a general theory of orthogonal or unitary representation. Direct sum of finite dimensional representations, finite or infinitely many, plus weakly mixing. Weakly mixing means just there's no more finite dimensional subrepresentation. By definition, no more, or one of equivalent definition, no more finite dimensional subrepresentation. And the direct sum of finite dimensional representations, finite or infinitely many, this part is called almost periodic. So the representation is decomposes into almost periodic part and weak mixing part. And accordingly, the B cocycle is, if there's a pi g invariant subspace, then the one can project onto pi g invariant subspace, and B also decomposes into B almost periodic part plus weak mixing part. This is a general part. And what is important is that if G is always it's finitely generated, but let's write it again. Finitely generated amenable group. And if there's a B such that almost periodic part is non-zero, but it's also harmonic because I don't want trivial cocycle in one coboundary, so it's harmonic. That is or in other words, it has non-trivial H1 bar reduced cohomology. Then G has virtually Z quotient. The reason is simple. If we may almost periodic parts are direct sum of finite representations. So finite dimensional representations, we may assume it's finite dimensional. And if pi g is infinite group, then it's alternative. There is a virtually Z quotient. In fact, most of the cases it appears. In fact, if pi g is finite, this is more often appears. But if pi g is finite, then the kernel pi is finite index. As finite index, and the pi b cocycle restricted to the kernel of pi g restricted to kernel pi is an additive map, additive character. Additive character. And because B was harmonic, B was unbounded, and so the restricted to finite index subgroup, it's still unbounded, so it's non-zero character. So you get anyway quotient onto Z from kernel pi. So we want to know the condition when AP is non-zero. almost periodic part is non-zero. So these are studied by Shalom in ACTA paper. So he first, I think this is really his motivation, that his observation was that if G is virtually nilpotent, then it has the property HFD. He termed it HFD. This is that any harmonic cocycle, any harmonic, any harmonic, is almost periodic. That is, it's the sum of finite dimensionals. And why this is interesting is that then if group is amenable, or HFD, that is a group, if group has HFD and the group is amenable, then you always get the partial quotient onto Z. And of course, by Gromov's theorem, virtual nilpotency is same as polynomial growth. And the Shalom's idea at that 2004, before Kleiner gave a second proof of Gromov's theorem, was that prove directly from polynomial growth to HFD. Then you get a new proof of Gromov's theorem because you get partial quotient onto Z. And this was done by me last 2 years ago. And other reasons, other interesting reasons that, so everything is Shalom. Other interesting reasons he considered this HFD is that amenable plus HFD is a quasi-symmetric invariant. And the example was that, so the conjecture, Gromov's theorem is that the virtual nilpotency is a QI invariant. And the conjecture is that the polynomial, polycyclic groups are QI invariant. That's both, one can say that the lattices in certain Lie groups are QI invariant. And in fact, Shalom proved that polycyclic groups have this example of HFD, have this HFD, so that any group quasi-symmetric to polycyclic group has at least virtual Z quotient. Or he proved Baum-Slack-Solita group, which is amenable Baum-Slack-Solita group, or Lampreiter group. Lampreiter group, I don't know which. You see the picture of which group acts on which. It's obvious, yeah? Otherwise it's interesting. This is it. And the non-examples are Z with product with Z. And the open problem, there are a lot of open cases which we don't know. The square Lampreiter group.
So non-example of HFD.
Oh.
It's a non-example.
Non-example of HFD, yes. Oh, yeah, and these are all, I'm talking about only amenable groups, and the people are so far interested only in amenable groups, HFD. A non-amenable group can have HFD, of course. For example, group with property P, then in fact there is no cocycle at all, so the definition of this any B is actually 0, so almost periodic. So it's trivially satisfies, and then you can do some allowed construction out of P product of something, etc., and can construct something. But that's all. So the HFD, so the one wants to know No, the criterion when B AP is non-zero. To be almost parodic or between mixing via random walk. So random walk xn is a trajectory of random walk, so it's S1, S2 to Sn, where the Si is a randomly chosen IID with mu distribution. Mu is a probability measure on G. Yep. Then the B, from now I generally assume B is harmonic. This implies that the Bxn, so this is a random variable, the probability measure we usually don't write down, but probability space is given by this, yeah? Or it's actually support S, doesn't matter. Then this is a martingale. This is a trivial, just what probabilists call it. That is, if I condition B n plus 1 step onto x1 to xn, which means that if you average over this, if you add t and you average over mu t, then you return to the same thing. And even more, so from these things, one can easily calculate like this form. This is I separate n step from the n minus 1 step. So b x n minus 1 t. I write important thing here. C. Then this is b x n minus 1 plus pi x bt. Okay, I write. And then this is a norm of this plus norm square of this, norm square of this, and the cos term. But the cos term is going to be 0 because B is harmonic. That's BT is 0. B harmonic. So that there's no cross term appears. That this and this inner product this with this and average over t is 0, no matter what xn minus 1 is. So this is E, and the average over t is do nothing on n minus 1 square, plus our expectation do nothing on this side because it's unitary or isometry. So this is a norm of B square norm of B. So I do NB. So this expectation is always a definite number n times norm of B, norm of square norm of B. Then although I don't use it, there's a field corollary by Erschler. Is that if one computes the expectation of this x and length, word length, this is one of the primary tag object of studying random walk theory, how fast it exits, how fast it goes to infinity. Is at least square. That's actually you can get rid of square, but let's say square. Then it's at least linear growth. If you get rid of square, then it's there's square root here. So there are always for any infinite group, there is a constant c, such that this length grows at least square root n. Because if group is amenable, then there is a such harmonic cocycle, and this applies. If group is not amenable, then this is easy to show. This grows at least linear. So for some c is constant because this value is dominated by xn length times maximum of b t. T is in S, that is with square. By this identity, cocycle identity. Okay. Then this from the one uses probability that if it's martingale, one expect there's a central limit theorem, and actually under the condition to apply Martingale's central limit theorem is quite restrictive. But in this case, everything works beautifully, and Martingale central limit theorem applies. That's so Martingale central limit theorem dx, and this is random variable in Hilbert space valued random variable. This converges weakly to something in distribution. So that B, that is any B in Hilbert space. This converges in distribution. So I took in actually a bit more precise, but I took inner product, and now it's just real valued. Here I use orthogonality because I don't want complex Martingale central limit theorem. A real valued on this random variable converges in distribution to normal distribution centered with variance, something variance. Where and variance, then one needs to compute variance of this, and in fact, this computation is really functional analytic. It's given by inner product of BB with respect to operator S, where the S is a Hilbert-Schmidt operator. Associated with P, BT tensor BT, where P is so if you don't understand here, no problem. Projection onto H tensor H, but invariant under G action, diagonal G action, which is a positive operator, and conjugation by invariant under conjugation by G. So the all eigenspaces, and these are Hilbert-Schmidt operator, so it's almost just matrix. Eigenspaces are finite dimensional, G invariant, and I write lambda 1, lambda 2, these are non-zero eigenvalues. Hilbert-Schmidt operators has it's diagonalizable and there are non-zero eigenvalues if it's non-zero. And the corresponding eigenvectors I assume they are orthonormal. That is it. I diagonalize S. Then one gets that this value Bi in distribution converges to normal of 0 lambda I. So that it's let's say to lambda I squared. So that it's up to how you write this is. I put sigma square there in the variance. So it's Gi. With Gi, GIs are standard normal distribution, but they are IID. They are IID because if I make a convex linear combination here, then everything it's still normal distribution and it behaves as if it's independent. So this is very independent IID. And one can compute the norm of this by Parseval formula. Is in distribution. Oh yeah, is sum of dxn di square I by Parseval formula, but there's a missing part. That's because Bi is eigenvectors of the non-zero eigenvalues. There are S is Hilbert-Schmidt operator may have kernel. Missing part coming from due to null space of S. And you work out what happens to this missing part. Then we arrive in this theorem, Erschler and myself, last year. That's where this converges in distribution or in moment or whatsoever it's saying to sum of lambda I, Gi square plus theta missing part. Missing part is a constant where theta is a constant such that non-negative constant such that the sum of lambda I plus theta is so that if I expect it, I get always the norm b square norm because of this. And I expect it, I get plus lambda I plus theta, and this has to be b square. So for example, accordingly, so the b is sum of almost periodic part plus weakly mixing part. And the B almost periodic part has norm sum of lambda I, and the weakly mixing part has norm theta, square norm theta. So if this is non-zero, this part is non-zero, this part is non-zero, you get the almost periodic part. And even you can see the multiplicity and you can tell the estimate of the dimensions, finite-dimensional representation. So the corollary is that the corollary BAP, B is BAP, if and only if theta is 0. This if and only if. So these are all non-negative, of course, because square non-negative, and these are Gaussian. So that if this is 0, if and only if it has it can take very small value. Probability of that dxn is less than c square root n limits is greater than 0 for any c small. Usually given cocycle, it's difficult to compute anything like this. In fact, we couldn't do anything computation. Anyways, so this gives us we wanted to solve at least one of these problems, but there are a lot of open problems. In particular, we didn't find any new example of HFD group, unfortunately. But open problem is that so first property is that I consider the property that limits property of random walk. Now I get rid of B. Property of random walk P that xn or not xn max of xk k is 1 to n is less than c square root n is greater than 0 for any c. This is stronger than this. Number 2 is that limit p just x and c square root n 0 for any c greater than 0. Now, third, so these are weaker conditions. Is that limit p xn is c square root n is 0 or n or some large c. So number 2 implies this implies HFT, the constant may be changed, but for all c, so it doesn't matter HFT. Number 3 is random walk people often consider this is called diffusive condition. For random walk on many nilpotent groups satisfy this. In fact, random walk on nilpotent group satisfies this stronger condition. So we call this condition that the random walk, at least some probability people does not leave the neighborhood of your hometown. We call it quotient. And the problem is that if they are equivalent, that's all examples, or there are a lot of examples which satisfies 3 and does not, which is not known if they satisfy HFD, etc. But the example of number 1 is that the virtually nilpotent group, so polynomial groups, or BS1n, or with product, the Lamplighter, and polycyclic group we couldn't decide. Non-example, of course this is square with product 0 by 2. So the proof of the condition 1 for Riesz product, Lamplighter, if you know what Lamplighter group is, it's simple. Lamplighter group is that on Z, this Lamplighter person moves, and sometimes it beats the lamp, and sometimes turn off the lamp. But then on Z or on any ZD, at least at some probability, this Lampreiter is confined, works only around the neighborhood of identity up to this scale. And then the turn right or turn, how many lights are turn on or turn off, the length of this word is that one moves just turn off and it's turn on. Moves here and it satisfies this. If group is Z square, this person still moves around the word of length at most C square root n, but there are more that the person visit more sites than square root n because there are square root n times square root n sites in the board. And in fact, person visit what it's known square root n log n sites expectedly, and so it cannot satisfy in this square case. It cannot satisfy. So the HFD is somehow is a restrictive condition. So how many time do I have? How much time do I have?
5 minutes.
What, 5? Okay. Okay, 7, even better. So this as I promised, I give an explicit construction cocycle. That's the final thing is that B, AP, beyond HFD, because HFD is so restrictive, many groups do not satisfy, but still you might find a virtual Z quotient on more general groups. One considers a cocycle. So I assume, in this section, I assume one can replace it and one can assume this. Assume mu square convolution over 1 over 2 square root exists. If doesn't exist, I replace mu with mu square. This avoids parity issue, which always appears in random walk. Then I consider the cocycle. This is mu square n over 2 minus g mu n over 2. This is, but I consider cocycle this of Hilbert space cocycle. Then the Cn 2 norm is some Cn g norm. This is normal. This is mu n1 2 times mu n1 minus mu n2. Is 2 mu n e minus mu n plus 1 e. So this is anyway it's calculable. And then the bng is a cng but normalized by 2 norm, Hilbert space norm. Now it's normalized, and I fix for any u alpha filter. So although I said it's explicit, I use ultra filter, but then actually in the end it disappears. Ultra filter on n, because clear ultra filter, I define the ultra limit as a cocycle. So if I take just the limit of this cocycle in this Hilbert space, they converge to 0. But I take ultra limit cocycle. So this is one coboundary. This is a trivial cocycle. But in the end, in the limit, one gets a cocycle. Cocycle relation is stable and with a product. And one does some calculation and checks that this B is harmonic cocycle, which is non-zero. with this norm is 2 with norm is 1. And then if one wonders if the norm of BG depends on the ultra filter I use, one used, that's the B, in fact, may depends on you, ultra filter. That's this is what Erschler's were working. That's some automata group. That's this when group is amenable. This is asymptotically invariant up to normalization in L2. But the speed of convergence she can control. There's a lot of several groups. One can control the speed of convergence, and in particular G1 to G2 the speed of convergence is something like this, and the other thing is the other part is grow fast, and then the ultra filter can look at this part or this part, and the cocycle may factor through G1 or may factor through G2, and so that may depend on mu if you find group. Okay? And so the BAP is non-zero. In the end, BAP is non-zero if and only theta is not 1. This is not 1. This is if and only dxm m minus 1 expectation of this limit always exists because it converges in distribution greater than 0. And then one plug in this construction and can tell what this is. So this, what's no? This is equal lim m, lim soup, no limit m to ultra filter expectation mu star n xm minus mu star n plus m e. If I expect this, it's 0. Mu n e minus mu star n plus m e absolute value. And the corollary, then there's a some certain convergence. In fact, this convergence is uniform with respect to mu u. That the space of ultra filter is compact, and you use still more functional analysis and say that this convergence is uniform with respect to u. That's if lim m, and I get something finitely statement n may not seem like finitely statement. This value is greater than 0, then G has virtual Z quotient. But unfortunately, this condition is almost impossible to verify. I verified it for polynomial growth group directly. That is, but I used the doubling condition, so really beyond that, it's not clear. That our hope was that if growth is smaller than some exponential, some function, then it might satisfy such condition, etc. But it was impossible to calculate. So, okay, so this is end. Thank you.
Thanks a lot. Other questions? So, when you said, the last thing you said that if you assume what kind of growth, the hope was
for polynomial growth, or just actually doubling condition, it's same. Then this here is a direct. But it's almost same. It's just it's just a bit more. It's just almost similar, but a bit more complicated than my proof 2 years ago. That's polynomial growth implies HF.
Do you think, I mean, there could be some kind of other instances where you actually, out of this, guarantee that there is a Z quotient?
Z quotient? No, it's everything is virtual system. Also, annoying part is that if group is the polynomial growth, then in fact B is finite dimensional. It's sum of, it's just B is really finite dimensional. Pi is finite dimensional. But I didn't see how to prove it. Otherwise, all go through polynomial growth implies virtually nilpotent, and virtually nilpotent case is finite dimensional.
And the last thing concerning something which is not on the blackboard anymore. I mean, so Mock proved the theorem for finitely presented groups.
Oh yes.
Right?
Actually, I wasn't interested in this business, but Anna Erschler read these old papers and we were not. So after all, the existence of this pi isn't a difficult result. It's just some limiting argument, clever limiting argument sometimes. And then the mock proved something which if we view in this way, it says this theorem. And clever Shalom proved something else, which if we look at in such a way, it tells this theorem. And Shalom, he was interested in reduced cohomology. His statement is exactly like that. And he also proved for all compactly generated locally compact groups.
Now, I thought that Mock said it explicitly. He has a paper where he does Hodge theory, right, and does a limiting argument like this.
Oh yeah, same limiting arguments are same. So it's interesting that some fair always there's a limiting argument.
Yes.
So maybe this was what Ron was asking. Could it be that finitely generated amenable groups always have a virtually Z?
No, they are simple finitely generated.
Okay.
And there are also torsion, that sub-exponential growth group with all elements are torsion. Then there is no virtue. So in particular such group, this is 0 and we don't know what it means.
So as I remember, your original result uses entropy type criteria. So but you get rid of entropy from here.
Yeah.
But can you state in terms of entropy?
Entropy somewhere.
I don't know. Yeah, somehow convergence of this, rate of convergence of this and that's related to entropy.
Okay, other questions? No? Well, let's thank Taka again.